take a look at this problem. So we have, yes, it is recording. Yeah, go right on. So we've got hydrogen gas, or hydrogen cyanide, HCN, and we're putting in OHs, right, NaOH. So what are our products? And cyanide, great. Very good. So they give us a Ka for this guy. And then they also tell us, all right, well, there's 50 milliliters of it. So we're going to need to know the moles that we're going to start with there, right? So 50 milliliters times 0.1 is 0.005 moles HCN. And we're going to be adding 0.1 molar NaOH. So they want us to calculate the pH and all that sort of stuff. So as we, at these different points, okay? So I'm just going to set up my ice table here. I'm just going to use that equation above here, and we'll kind of go from there. We got 0.005 moles of HCN to start. 8 milliliters times 0.1, what is that, 0.0008? Right, water is whatever, 0. So minus 0.0008. Okay, so we have a buffer now, right? We have HCN and the conjugate in solution. So because we have a buffer, what equation can we use? The Henderson-Hasselbalch, yep. So we're going pH equals pKa plus the log of our base, which is 0.008, over our acid, 0.0042. So all that is going to be equal to negative log of 6.2 to the negative 10 plus the log of 0.008 divided by 0.008. Well, I got 8.487 for our pH. Okay, great. So that's pretty much what they got there as well. All right, so that was good. So at the halfway point of the titration, what point is that? Yeah. Why does pH equal pKa at this point? Yeah, we got the same amount. Halfway, we have the same amount of HCN to Cn minus in solution. So that log expression of those guys are going to 0. That goes to 0, right? That's because this is the half equivalence point, right? This is the half equivalence point. As always, sounding that out. Okay, so the half equivalence point. So the pH equals the pKa, right? So that's just equal to minus the log of 6.2 times 10 to the minus 10. So that was 9.207. Actually, 08, 9.208. And that is pretty much the answer there, 9.21. Okay. All right, so that's the halfway point. So that means that we've added enough hydroxide in order to have the same amount of our acid and our conjugate in solution. So that's very nice, easy calculation to do there. And the equivalence point. So what's the deal with the equivalence point? What has happened at this point, at the equivalence point? What? So, yeah, we've neutralized the whole thing, right? We neutralized all the HCN. If that's the case, what did all the HCN turn into? The CN minus, right? So only thing, the only so HCN is now all CN minus, right? That's the only stuff we have floating around in solution right now is CN minus, right? And H2O. That's all we got in solution at the equivalence point. We converted it all into CN minus and water, okay? All right, so that means we can just skip to our weak base problem here, right? This is just a weak base problem. So what we need to know, though, is we need to know what the concentration of CN minus is in solution, though. Right? We do need to know that. We got to know what the concentration of CN minus. If we're going to do a weak base problem, we've got to know CN minus. We also need to know Kb, right? We need to know Kb because we have an expression here with OH minuses being made. So we've got to have a Kb for this, right? So Kb is easy, right? That one's Kw over Ka. So that's just 1 times 10 to the minus 14 divided by the 6.2 times 10 to the minus 10 number. So that is 1.613 times 10 to the minus 5. Okay, but how can we find the concentration of CN floating around in solution? Yes, sir. Yeah, the moles of CN over the total amount of liters of the solution. So we've got 0.005 moles of it. What's the new volume of our solution? What should be the volume of our solution at this point? How much NaOH, like if you go back up to the top here and you look at the problem, how much NaOH, what volume of NaOH am I going to need to add to that solution to neutralize it? How do you know that? Yeah, they made it very easy on us here, right? The concentrations are identical. So if we have 50 milliliters of acid, well, it's going to take 50 milliliters of the same concentration of base. So what's my new volume then? 100 milliliters, right? So we can just take that, 0.1 liters. So our new concentration is 0.05 molar. All right, so I'm going to move this over just a hair so I have enough space. Right, because we just have to run our weak base problem here. All right, because X is going to be equal to our concentration of OH. So I got it equal to 8.98 times 10 to the minus 4. So POH. Is that right? Yeah, maybe it is. 3.047. So pH is equal to 14 minus that number, 10.953. Okay. Okay, so the important points there, half equivalence point and equivalence point. Okay, we can kind of skip doing some of the ice table and stuff if we understand what's happening at each of those points. And we can just jump to the weak base ice table rather than running through. All right, so we'll take a look at some of this stuff a little bit more in terms of kind of, we're going to try and draw a couple things here. All right, so the second part of this lesson is all about titration curves. All right, so we're looking at titration curves and like what these things look like graphically, and pH versus the volume added and all that sort of stuff, just like you guys made on the continuing variations lab. Okay, you guys were plotting, what you guys were doing, temperature and volume. We could also look at, you guys are going to do a titration next week, a couple of them, and you're going to plot the pH as the titration happens and stuff. Okay, so there's three different differences. There's three key differences between a strong titration and a weak, strong titration. So, and what we have going on here is we have a weak acid being titrated by a strong base for this one. And there's some very important parts of this graph. All right, number one that I tend to like to start with here first is the equivalence point. Here's the equivalence point, right? Notice pH is. Okay. It's not 7. It's greater than 7 for this one, right? If it's a weak, strong titrations are going to have pHs that are going to either be greater than or less than 7. Right? Because remember, what's present at the equivalence point? It's the conjugate and water. That's the only thing that's present at the equivalence point. Right? Just like how we looked at just above, right? At the equivalence point, the only thing that was left was the conjugate and water. So we had a basic sort of situation there. And the opposite could be true, right? So when we look at these, if you got a weak, strong situation for the equivalence point, pH is either going to be greater than or less than 7. Because what's the equivalence point for strong? It's always 7, right? If you have a strong acid and a strong base and you react them together, the only thing you're creating that's salt and water, right? But that salt is neutral. That's going to be a neutral salt that you make. And water. So really all you got is water floating around. So if it's strong, it's always 7. At the equivalence point. That's a very key component in trying to identify what kind of titration curve you have. All right. The other component here, if we look at the steep initial rise, okay, that's this part right here, and this component. We'll talk about both of those. Okay, initially, right when you start adding, like here, we only had weak acid in solution, right? So right when we start adding the base, we set up the buffer, but right initially, it's going to have a very quick rise in pH. Okay, so it rises quickly, but then levels off. Okay, because you create a buffer. When you titrate a weak acid or a weak base with another strong guy, like in this case, when we titrate that weak acid with a strong base here, so we have HA, we're adding OH to it, you get A minus and water, right? Okay, so as you're adding the OHs, you start creating A minuses. So then you set up the buffer. Then you get a buffer in solution so that the pH stays pretty constant then. Okay? So you get a nice flat little area there of the graph. Okay. And then the last one is really just kind of indicating whether what you have here in terms of if you have a strong acid, the initial pH is going to be very, very low. Okay, if you only have HCl or H2SO4 or whatever, they totally dissociate. And the pH is dependent on concentration of H plus in solution. So if you have a strong acid, typically the initial starting pH is going to be much less than 1.5. Okay? Where if you have a weak acid, the pH more than likely is going to be greater than 1.5. So like we have here in this graph, like the initial pH starts there at, right? It's starting there at 2. Above 2, right? It's right here. Okay? So that's what, that kind of can give you an indication of whether you have a weak acid or a strong acid in there. And the base works kind of very similar. If you have a strong base, that initial pH is going to be greater than 12.5. And if it's weak, that pH will be less than 12.5 or thereabout. And this should say initially. Okay. That helps you identify what you have going on in solution. Okay, so let's do a little drawing here. We're going to try this out. We're going to draw a titration at molecular level. We're going to assume we got, I'm just going to put this down a little bit. We'll say we got 6 moles of HA, and we're adding OH to it. Okay, so we draw out our flask. So our flask, and we have 6 moles of HA. 2, 3, 4, 5.
I would change it to 4. Let's quickly change it to 4.
Oh, this is all right. Now I'm in it. Now I'm in with 6 here. Right, we got our burette up here, and it's got NaOH in it. Right, it's got OHs. Okay. What? It's fantastic, actually. Yeah. And I can't believe I didn't come up with that one. That's a good one.
You can have it.
All right, so I've got 6 moles of HA, right? We've got 0 moles of OH minus, and we got 0 moles of A minus, right? There's none of that going on. Okay? Let's go to the half equivalence point. So at the half equivalence point, what do we have in our flask now? I'm going to draw my 6 HAs. That one's messed up. I'll just get that one out of the way. Let's just start adding OHs, right? For every OH I put in, I cancel out an HA and make water and A minus, right? So, all right, so I want to get there halfway, so I got water and A minus, right? Water and A minus. I'm making noises for your entertainment. A minus. Now I'm done, right? I'm at the half equivalence point, right? I'm at the half equivalence point. Because I have 3 moles of HA, I don't have any moles of OH minus sitting in solution. I'm talking about in solution right now. Okay, I added 3 moles of OH minus, but they were neutralized. And now I have 3 moles of A minus. Okay, so do you see how that, we have a buffer now, right? You can use Henderson-Hasselbalch here because we have both an acid and a weak acid and base in solution, so we can use the Henderson-Hasselbalch. All right, what about at the equivalence point? I'm going to draw 2 more scenarios here. My glass got really deformed. All right, so for every OH I add, I make a water an A minus. And there I am. I made it to the equivalence point. There's no HA left. There is no hydroxide left in solution, but we now have 6 A minuses in solution at the equivalence point. So we've turned it all into the conjugate at this point. All A minus. Okay? That helps us kind of visualize what's going on here when we do a titration. All right, so pH is going to totally depend on, right? pH depends on that, right? Right, and now the very last point here, at any point thereafter, right? Erase this. And just to kind of finish this up, at any point thereafter, I'm off the screen, am I not? All right, at any point after, what are we going to have sitting around in solution? We're going to have A minus, right? We got 6 A minuses floating here. But what are we going to have, at any point after, what are we adding in solution now? Straight up hydroxide, right? Okay, we're just going to add in more and more hydroxide. So in this case, we got 3 moles of OH minus. We might have 6 moles of A minus, but it's weak, right? We still have 0 moles of HA. Right, this guy's kind of weak, right? So pH is dependent on the excess that we have in there. All right. So that's when you get that steep pH change. Okay, when you're doing the titration, right around the equivalence point. Like once we pass the equivalence point, you just start dropping in OH minuses. And so the concentration of OH minus in solution skyrockets. Right? It goes from 0 or just a tiny fraction of that A minus, right? The weak base can make a tiny fraction of it in solution, right? But once you start dropping in OHs past the equivalence point, that's the only thing. Concentration of OH minus goes way up, so the pH skyrockets. And that's why the equivalence point is so steep right around there. Okay? That's why it's so steep on that hill. Okay, so if you look on the next page, flip it over here, we got the different scenarios. Right, we have the different scenarios here with our strong acids and bases. Right, if you got strong acid, strong base, I mean, as you get real close to the equivalence point of a strong acid, strong base, you go from having H pluses, couple H pluses left over in solution to same amount, which so it's all water, to all, then all of a sudden, only thing you got in there is hydroxides after that, right? So that's why the pH changes so drastically there once you get close, okay? So strong is always at that, right, 7. We're here at that 7 pH for strong at our equivalence point. And notice here, if we have a weak acid, notice how high it starts up in comparison to the strong acid. That's what I was talking about, that initial pH. All right, and then the equivalence point up in here. So it looks like right around 8 for that one. Right around 5 for that one over there, okay? So the weak base being titrated with the strong acid, that sort of stuff, okay? So when the equivalence point is not at 7, you have a weak, strong titration happening, okay? And you can see how the curves are a little different. See how those ones are pretty smooth, just like that nice S, where the ones down below, they start to go, and then they level off for a little bit. There's that buffer situation happening, okay? Resisting the change in pH. All right, so I'm going to keep going. We just have some more examples of what titration graphs look like. Some other examples here. You have a polyprotic one, a polyprotic acid for this one here, right? You can see you got the equivalence point, but you also have 2 buffer regions on that one. This is a good example of this one here. You've got, if you keep going on the next page, and right there, you've got 3 equivalence points, right? That's maybe this is H3PO4, right? Where you've got 3 H's to titrate, so you've got multiple steps going up. All right, another polyprotic acid, right? That's kind of an example of that. And this one right here is one that I really like. This graph here is a nice graph, and it kind of what I was drawing out a little bit, except this one shows you a polyprotic acid, like half equivalence point. You have 50% of each of the acid and its conjugate base in solution. And once you reach the equivalence point, sometimes you'll see the equivalence point will also be called the isoelectric point. They call it the isoelectric point sometimes as well. All right. It all gets converted into one thing, and then the next equivalence point. So this is the second half equivalence point right here, and the second equivalence point. Everything's been converted all the way to HA minus, or to A minus there. Okay, all the way to the conjugate. That's a good little graph. Okay. All right. So if we keep on moving, this is where we get to indicators. All right, when we're looking for indicators, why we use phenolphthalein, why we use methyl red and some of these things, you can see up at the top of the scale here, right, you've got pH up here at the top. It's a little hard to see, but it's there. Okay, and we want to choose different indicators based on where they're going to change their colors. Okay, on the pH where they're going to change their color. So, and you can see, like, remember how so if we look, phenolphthalein is the one we're most familiar with, right? This guy right down here. Okay, phenolphthalein, we're most familiar with it. You got to remember, it's the way they look here. Like this one here, you guys know any basic solution is going to be pink, right? It's not just pink around 9 or 10. Like if it's 14, it's going to be pink, right? And then it's clear after, phenolphthaleine's clear after like 8. It goes totally clear, okay? All right, so these kind of, the colors of these guys expand out. Like for some of these here, like you can see is that thymal blue? Yeah, thymal blue up here at the top, right? It's blue. Thymal blue is kind of neat. It can give you two spots, right? It's blue all the way through here until you get to around 8, all right? And then once after that, it's yellow all the way until you get to around 2.5 on the pH. Once it turns that acidic, then it turns red, Okay, so when these indicators change colors just by either getting pronated, like getting attached with an H plus or something like that, because there's a high enough concentration around that it'll attach, or it's so basic it lets it go. All right, and it will change color with just a slight little change. You guys can make your own indicators at home if you wanted. You go to the Jewel, you get some red cabbage, that purple cabbage, chuck it in a blender, throw some water in, blend it up, and then you can play around with it. It's awesome. It works great. It's got all these indicators in it, so it's like a universal indicator. Red is acidic, and it goes all the way up to blue for being basic. It's fantastic. It's awesome. I'll bring some in Monday. Yeah. You guys can play around a little bit. It works great. It works really, really good. Pretty cool. Okay. Don't worry about it. I'll get it from Foods or something. So, but we need a blender, though. I mean, so I'm not kidding. So I'll have to get it from Foods or something. I don't want to lug it from home. So, right? But indicators are really, really interesting. All right? So, like here, if you look at that first question, they're like, all right, well, the pH is at an equivalence point of 5.37. All right, if that's the case, right, that's somewhere right around in here, right? Okay, so if it's at 5.37, we want to pick an indicator that's going to change color close to that pH, right? So if we look at those, all right, so we've got a couple of these. We've got the bromocresol green is going to be blue all the way until about 4.5, and then it turns yellow after 4, and so on, right? The methyl red is going to be yellow, and then it starts changing color right around 5 into that, starts going from yellow, kind of that pinkish red, okay? And then there's the black tea, which is blue, and then it turns about 6. So that's why in this one, we probably want to choose methyl red, because our indicator color change is going to be right around that pH that we're desired for, that we're looking for, okay? All right, so one of the things that we could use, like, you know how we always do that strong little big lab or whatever, where we're mixing NaOH and HCl and you got to bring a neutral solution together, okay, and that sort of one, right? We always use phenolphthalein, right? If you look at phenolphthalein, it changes pH, it changes color right around 8, right? Okay, but you guys are trying to make a neutral solution. So you're better on, and we kind of err on the side of it being too basic, all right, a little bit, because the bromothiamyl blue isn't always like a very nice indicator to deal with, right? We don't want that one just being kind of out and about necessarily, all right? But also remember at the equivalence point how steep it is, right? So if I add just a drop or two, and I give you some leeway, that drop or two is enough to make it change, because the equivalence point is so steep that we can change the pH real drastically, like going from like 10 to 6, just on a couple drops, if your solution is pretty much right around neutral. You know what I mean? Okay. But there's an easy cheat for that lab, but I'm not going to share it with you.
We're not going to have to memorize the table, are we?
Not at all. Not at all. No. A lot of times you're going to be asked to be like, all right, well, here are some indicators, and here are their pH values, or their Ka values. Tell us which one would work best. That sort of stuff. Okay. And you'll kind of get the feeling for that. Like this one here, right, this next one. Right, bromothiamyl blue has a Ka of 1.0 times 10 to the minus 7. It's yellow, and then you put a few drops indicator in a strong acidic solution. If the solution is saturated, it's titrated with NaOH, what will the pH? At what pH will the pH color change first become visible? So if you look at bromothiamyl blue, right, it's going from, I mean, like right here, this guy, this is bromothiamyl blue. All right, so around 6.5 or so, 6.5, it starts to change from blue to that like green, and then it'll go yellow. Okay, and that sort of thing. So universal indicator is something I'll do a little demo on Monday too with universal indicator. it has multiple indicators in it, so it will change color all the way from, it can represent every pH basically along the way, because it's got like, no, this is a liquid. So it's a solution of a mixture of a bunch of different ones. I think it's got crystal violet, thymo blue, methyl orange, methyl red, phenol red, phenolphthalein, and I feel like there's one more in there. One more blue one. One more on the far end of that, but I don't see it on the list. That gives us a nice pink or a nice purple color when it's really basic. It's pretty cool. But yeah, there you go. That's it. That's all for today. We're done. So I have.